So this is a first short tutorial to look at how we can use power and virtual work to figure out speed and torque ratios in a machine, for example, something with a set of gears. So let's first just talk about it in a general way. Remember that power is force times velocity, or for something with angular motion, it would be torque times angular velocity. And virtual work is looking at power for a short instant of time. So it'd be force times some small motion, dx, or torque times some small rotation, d theta. So here we are. We have some machine. And, whoops, I somehow went forward 2 slides. Let me put it into black mode. And I have some machine here. And we don't want to think about the details, what's inside this machine. All we want to care about right now is what's going to be the relationship between some force that I apply at the handle. I'll call this F1. And a motion allowing me to lift a weight down here by some small amount, which I'll call dy2. Okay? Well, what we know is that the weight has a force due to gravity. And that's my output force. And so I'm moving a small amount dy2. So my virtual work is this force times this small motion. And what's on the input side is that I have some small motion of the handle. I'll call that dy1. And if nothing is lost, then I could write that the force times dy1, I'll put a little dot there to show that there's multiplication, is equal to F2, that's F1, F2 times dy2. But in fact, the machine is not, so this would be if no loss. If no loss. But in fact, there is some loss, and some power or some work will be lost. So it would either be power, or if we're talking about virtual work, it'll be power times some small amount of time dt. So in the more general case, we would say F times dy1 minus power loss times dt is equal to F2 times dy2. And this is, in one slide, basically captures a lot of what we're going to be covering in this course. We'll be building devices, crawlers, for example, that have interior gear trains, and we'll be looking at how much power or how much energy gets lost inside the transmission, and then we'll be looking at the output as a function of the input. So let's go to the next slide and show how we can use this idea of power and work to solve some simple problems. And let's see, I have to clear and then go to the next slide. All right. So what I have here is a very simple machine. It's a lever. And if I were to ask you for a given weight, so we have a force here, we'll call this mg, is the force from that weight. Let's go ahead and make a coordinate system. I'll switch colors here to blue. So we have x and y coordinate system. I have an origin here, I'll call that O. And remember, this is a general motion in the plane, so there could also be rotations. I'll call that theta, all right? And if I said, well, look, for this machine here, if the weight is mg, what is my input force? I'll call this Fy1. What does that have to be? Well, one way, the standard way to do this would be to say, let's do a force and moment balance. We'll do a free body diagram on this lever, and we'll just solve. So we know that, for example, the sum of the forces in the x direction has to be equal to 0. Well, in fact, there are no forces in the x direction, so that's automatically true. Things are a little more interesting in the y direction. So some forces in the y direction, and we do a force balance. And what do we have? We have a force Fy1, and that's downward, so it's in the negative y direction, downward. Therefore, I give it a minus sign. And I have the force from mg, also downward, give it a minus sign. And then for equilibrium, there must be some reaction force on the fulcrum. I'll call that Ry, and that's upward. So plus Ry equal to 0. And finally, we have to take a moment about the point O, about the origin. So we also know that the sum of moments about O has got to come out to be 0. So what moments do we have? If we use the right-hand rule, then this force Fy is going to be acting with that lever arm L1 to produce an anti-clockwise torque, so that's going to be positive. So we'll have Fy1 times L1, and it's going this way, anti-clockwise, so I give it a positive. What else do we have? We have the torque from the moment. So we have mg, and that's multiplied by L2, and it's going the other way, so it gets a minus. And are there any other torques? Nope, because Ry, my reaction force, is at the origin. And so, in the end, we can solve to say that so Fy1 has to be equal to L2 over L1 times mg. So that's pretty simple, and we get the answer fairly quickly. Now, we could do this same problem by treating it as a machine with power. So let's now look at it using power or using virtual work. Okay, so here's our same lever again, only now we think of it in terms of an input and an output. So I have, again, my force Fy1, and the lever has to go downward by a small amount. I'll call this, say, dy1. And meanwhile, the mass is raised by also a small amount. I'll call that dy2, shall we say. And the force, again, from the mass, it's the same. It's got the gravity force mg. All right. Well, what I can say is that the input virtual work has to be equal to the output work. So therefore, Fy1 times dy1 has to be equal to mg times dy2. And this means that if I find a relationship between d1 and dy2, I can solve for my force as a function of mg. Well, that's not too hard to do. By inspection, we see we've got similar triangles. I have a long triangle here, and I have another long triangle here. And what I can see is that dy1 over dy2 has to be equal to L1 over L2. So now if I take these two expressions, this one, and combine them, once again I can solve. Fy1 has to be equal to L2 over L1 times mg. So this perhaps looks like not much less work than doing the free body diagram. However, the interesting thing is that I never had to solve for the reaction force, Ry. It doesn't appear anywhere in this expression, and that's because Ry does no work. There's no motion associated with Ry, and so it drops out. We only care about the input and the output, and that's sort of the secret to this whole virtual work approach. And it gets much more interesting when we take a more complicated example. So here's a compound example, and it's somewhat more complicated. I have now a lever Same lever as before. But it's connected to a rope through a block and tackle system, which is raising a weight. And we're going to use the same approach as before. We're going to say, okay, the weight force, whoops, let me go back. The weight force mg, I have to be into writing mode, mg, and the weight is due to the action of the lever, it raises up a little bit. So let's draw that. I'll call that, this is my output motion, dy3. Okay, and that's due to this pulley coming up as the rope gets taken up by the lever. The lever goes down a certain amount. I'll call that dy2, because what I'm doing now, I have to push up on the lever to make this machine work. The amount that I push up, I'll call dy1. And my force now is Fy1. So what do we have? We say that the input is equal to the output. Therefore, Fy1 times dy1 has to be equal to mg times dy3. So if we know mg and we're trying to solve for Fy1, all we have to do is find the relationship between dy1 and dy3. And the thing is that with a machine like this, you can often just do it by inspection. So what do we know? We know that if the weight goes up a little bit, in order to get the weight to rise, say 1 inch, we actually have to take up 2 inches worth of rope, because there's rope on this side and also on this side. And that's what we're pulling on with the lever. So from inspection, and in a real machine you could actually just measure it, or if you had a CAD program you could simulate it, or you could use a ruler and work it out by similar triangles and other ways. By inspection we say, okay, dy2 has to be equal to 2 times dy3. And that's why block and tackles work. You have to take up twice as much rope, but you turns out that you also double the force, because you have force on both of these ropes. And then again, as in the previous lever, we have that dy1 has to be equal to L1 over L2 times dy2. So finally, we can solve that Fy1 is equal to mg times dy3 over dy1, which turns out to be equal to mg times L2 over 2L1. So this is a useful machine, because if we have a fairly heavy weight, we get to multiply it by the ratio of L2 over L1. L1's bigger than L2, and we have a factor of 2 in the denominator, so we don't need as much force out here as we need to lift the weight directly. And what you see we've been doing here is, all we've been doing is we've been saying that the input work, which is F times dy, has got to be equal to the output, in this case mg times dy3. By balancing them and figuring out the ratios of motion, we can get the forces.